Welcome to the lecture on Advanced Process Parsing Techniques in NLP. In Advanced Parsing Techniques, we will be seeing the main parsers like CKY, dependency, and early parsing, and how to calculate the probabilistic context-free grammar. So first, before going into the concept of the particular process parsing, so we will see the definition of it. Parsing is the process of analyzing the grammatical structure of a sentence according to a formal grammar. It is a foundational task in natural language processing. So it's a basic task in NLP. So what the parser produces? It produces sequence of words as input. Sorry, it takes sequence of words as input and outputs a structured representation in a form of a parse tree or a dependency graph. So this creates the relationships between words. So how each and every word is related to each other. That can be understood based on this parse tree or a dependency graph. So why this parsing matters? Why we require this? Parsing is a critical building block. It's used in wide range of NLP applications. So without understanding the core structure or the sentence structure, we cannot interpret the meaning. So the machine translation is one of the key applications where parsing has been used, where you have to know the accurate cross language mapping. And in question answering part, where the you should know which are the subjects, which are the verbs, which are we to, and you have to extract the particular answer properly. So in that case we need parsing. And similarly, speech recognition, where syntactic context improves transcription accuracy. And then information extraction and text summarization, where it guides the extraction by key facts and relationships. So in these cases, parsing has a wide range of application. So now we'll go in my previous lecture you might have seen the basic how to draw the parse tree. There are two types of parsing, top down and bottom up parsing. So that basics I am not coming into in this lecture. We are just going to see the parsing called CKY parsing. CKY means Cocky Kasami Younger algorithm, is a classic bottom-up dynamic programming parser. It is one of the most widely studied algorithms in computational linguistics. So in CKY parsing, the particular grammar, the grammar content and all is there in the previous lecture. You can just go through that. So first, the grammar, the rule should be in CNF. CNF is Chomsky normal form. Those who have studied compiler design will know about the Chomsky normal form. So it should be in this rule. Either it should be the non-terminals, that is must, or you have a production rule with the non-terminals or with the terminal. So that if it is satisfying, then your grammar is in CNF. So once it is in CNF, you can go with CKY parsing. Then this algorithm builds parse constituents by bottom-up strategy, and it also uses dynamic programming table. So you will create a table, triangular table to avoid redundant computation, and it achieves order of n cube time complexity. So this is how we'll construct the table. This is the steps in which you construct the table for CKY parsing. It fills the triangular chart where cell of I, j stores the non-terminals and can derive the substring from position I to j. So it fills diagonal, combine the cells, propagate up, and it will check for the start symbol. So once the start is reached, then your particular sentence is grammatically valid. So if the start symbol appears in the top cell of the table, the sentence is grammatically valid according to the context-free grammar. The table also encodes all possible parse trees for ambiguous sentences. Even if you have ambiguous sentences, the table encodes all the possible parse trees. So this is one example. You have a grammar. A sentence comprises of noun phrase and verb phrase. Verb phrase is verb and noun phrase. So the sentence is we eat sushi. So how will you draw the parsing algorithm is, so first thing is sentence is divided into NP and VP. You put the sentence in the right corner. And then verb phrase is again divided into verb and NP. So in the corners, if you see NP, that will match to V, W-E-V. Verb is eat. Sushi is noun phrase. Okay, so the particular leaf nodes has the sentence, and if you propagate up you will reach the start symbol. Once if you reach the start symbol, then this particular sentence is in context free grammar. So that's what your main thing is. It is grammatically valid for the given CFG. So if it is like this, then it is grammatically valid for different CFGs. Next one is dependency parsing. Dependency parsing represents grammatical relationships between words directly rather than through phrase structure. Each word in a sentence is connected to the head word via a directed arc called the dependency relation. So, one of the word is taken as a root, typically the main verb. All other words dependent on the head word. Relations are labeled as NSUBJ, DOBJ, determiner. The result is directed acyclic graph. So what is the key contrast with CFG is, unlike parse tree structures, dependency trees do not have intermediate parse nodes, only direct word-to-word relationships, making them more compact and linguistically initiative. So what happens is, in parse tree, there are many intermediate nodes and you will finally reach the leaf nodes. The leaf nodes will have the sentence formation. But here there is no intermediate parse nodes, only direct word-to-word relationship in the dependency parsing. So if you see this example, in a dependency tree, arcs connect words to a syntactic heads. Each arc is labeled with a grammatical function of the dependent word. So verb is chases, the sentence is actually the dog quickly chases the cat. Okay, or else the sentence can be the dog chases the cat quickly. Okay, this is the sentence. So the root verb, if you remove the word chases, then you can see the dog quickly cat the cat, or else the dog cat quickly. So it won't have any meaning. So whichever verb which combines the two part of the sentences, that you have to take it as a root verb. So the root verb chases governs all other words. So the dependency labels such as NSUBJ is nominal subject, DOBJ is direct object. It makes the grammatical roles explicit and machine readable. The is determiner. Quickly is adverb modifier. So quickly is mainly it's an adjective type where you will just give an emphasis on a particular word. So this is a dependency tree. You can draw like this also, and you can see the next example. You can draw like this also. So here if you see what can be the root word is, I prefer the morning flight through Denver. This is the sentence. So here if I remove prefer word, I the morning flight through Denver, or else if I remove morning, I prefer the flight during Denver, or else if I remove Denver, then I prefer the morning flight through something. It's a space. So, but if I am not using the word prefer, we don't have the meaning of the sentence. So that particular verb is taken as a root. Prefer is taken as a root. Then you can draw like this also, how each and every word is related. So nominal subject, direct object, the is the determiner, and morning is the noun modifier, flight is a noun modifier, through any case, because the Denver can be any name, so any place, so it refers. So like this also you can draw the dependency graph. So where we use this particular dependency graph? Dependency parsing is used in mission translation, sentiment analysis, chatbots, and question answering. So mostly all the parsers, mainly it is used in mission translation, question answering part it is mainly used. Other than that, you can also use in sentiment analysis and chatbots. Next topic is early parsing. This early parser is introduced by J. Early in 1970, which is a top-down dynamic parsing algorithm. So if you compare CKY and early parsing, CKY is a bottom-up parsing technique, and early parsing is a top-down dynamic programming algorithm that can handle any type of context-free grammars, including ambiguous and left recursive grammars that challenge other parsers. This can be used for ambiguous sentences, left recursive grammars also. So there is no particular rule that it has to be in Chomsky normal form or something. So that is one key advantage here. So it does not require the grammar to be in CNF. It works directly with the arbitrary CFGs, making it as highly flexible. Runs in order of n3 for ambiguous grammars, n square for unambiguous grammars, and order of n for practical grammars, making it efficient for the real world use. So if a particular sentence have a practical grammatical sentence, then its complexity is order of n. Only if it is ambiguous, then it goes to order of n cube. So early passes, these are the three core operations. Early algorithm maintains a set of early items, dotted rules. We will see the dotted rules, how it progress. So three main core operations are there: predictor, scanner, and completer. Predictor, what it will do is it will add the new early items for the rules, whether it is matching the current location or not, and it expands the non-terminals top down. Scanner, it scans the or advances the items for the next input word matches the expected terminal symbol. Completer advances the items in the norm terminal as fully recognized, propagating the complete. What it will do is complications and the backup to this chart. So what it will do, it will once you say for complete a particular word, then it goes and starts with the next word. So it happens like that. So three core operations: predictor, scanner, and completer. So this is the example. We are taking one example here to explain the step-by-step procedure of early parsing. One is dog chases the cat. This is the sentence. So first you can see there the particular table is divided into operation types, production rules, and completed status. So here in operation types you have first initialization. Put the sentence. The grammar is given at the side. The sentence is comprising of noun phrase and verb phrase. So that you are writing and put a dot or dot operator in front of the noun phrase. Okay. Then your first step is predict. So what when you are going to predict NP, you are taking that particular noun phrase. The noun phrase can be either determiner N or it can be N. So in this particular sentence, first itself there is a word called dog. Dog is a noun. If there is a word the dog, then we can go for the first determiner and noun. Now it starts with only dog, so it's a noun. So when you scan dog, it is automatically noun phrase with noun phrase which gives noun. Okay, so noun and the dot is moved to this side. Okay, so the you are completing, you are scanning the dog word, then you complete it. Once you complete it, the dot in the initializations, the first sentence, that it is moving to np dot. Now vp. So vp you are predicting. So there is a v or np because we need a verb. Again there is a noun phrase the cat. Okay, so v dot np, that is the scan. So it scan the chases word and then it predicts. So when v dot np, then it predicts that dot determiner n or dot n. In that case, we require dot determiner n because after chases there is a word the cat. The is a determiner. Okay. Then you scan the. So determiner dot n. And then np determiner dot n. Then you scan the word cat. Okay. Cat is a noun. So that also fourth word also scanned is finished and then you complete it. So yes, NP dot VP. So one complete will be there once you complete noun phrase and after you complete the whole sentence, the verb phrase also. Okay, so this is the step in which you will do the early parsing. Only thing the dot operator you move and the three core operations you will do was scan, predict and complete. The next grammar is probabilistic context-free grammar (PCFG). It extends a standard CFG by assigning a probability to each production rule. These probabilities reflect how likely each rule is used. Typically, if you estimated the annotated pen tree bank, if you see that um, this particular probabilities will assign some probability value and it will have a score parse tree and then you will select the best parse tree, whichever has the highest probability it will be selected as the best parse tree. So here if you see, consider the ambiguous sentence. Any ambiguous sentence if you consider, there will be two parse trees, parse tree A and parse tree B. If you assign some probability value for sentence as zero point 0.9, noun phrase as zero point 0.5, verb phrase as 0.3, if you multiply zero point 0.9 into zero point 0.5 into zero point 0.3, you will get some joint probability. Similarly, for the other parse tree, you have zero point 0.9, zero point 0.5 and zero point 0.6 because the preposition is not there. So we have increased some values you have given. So that is joint prob when you multiply that joint probability you get 0.270. The parser selects parse tree because it has higher probability. So when you have ambiguous sentences, so then what you can do is, then anyway you know that you will be drawing two different types of parse trees. So when you draw two different types of parse trees, some probability value will be assigned to each particular grammar and then you multiply that, whichever has the highest probability you will select that parse tree as the correct one, so that sentence will be taken. So PCFG makes disambiguation principled and data driven. That is the main use of PCFG. So here one example we will see, John ate a cake is the sentence. So the probability is given here. We have taken one for the sentence, NP zero point 0.6 for proper noun zero point 0.4, verb phrase zero point 0.7, verb it's zero point 0.3, determiner zero point 0.5, determiner zero point 0.5. Like this we have initialized. Then you draw the parse tree. John ate the cake for a sentence is divided into noun phrase and verb phrase. You can see the parse tree in the red colored one. And noun phrase is proper noun. So John. Then verb phrase is verb and NP. Verb is ate. NP is determiner and noun. Your cake. Okay. All that you know how to draw the parse tree. Now based on the values given for the probability, you assign the probability in a square bracket as 1.0 for a sentence. Noun phrase is zero point 0.4. Now proper noun is 1, uh, then zero point 0.7 for verb phrase, for 1 for verb, np zero point 0.6, determiner zero point 0.5, np zero point 0.5, like that you assign the probability value. Okay, once you assign the probability value, then you multiply the rule probabilities 1.4 into zero point 0.4 into 1, all the values you multiply into 7.7 into 1 into zero point 0.6 into zero point 0.5 and zero point 0.5. So you get a probability of 0.02. If this particular sentence have an ambiguous sentence, then there will be another parse tree. So for that you will multiply and find out the probability value. Whichever probability is higher, then that is the proper tree which you can take for a next step of data driven responsibilities. Okay, so this is PCFG. So why we use PCFG is to resolve ambiguity, to improve accuracy and to learn the rules which are all there from the tree banks using maximum likelihood estimation. So for that you can use this particular PCFG. So it mainly for ambiguous grammars, this will help, it will be very helpful. Okay, so when multiple parse trees are valid, then you can go with PCFG to choose one particular parse tree. So the comparison of the parsing techniques, CKY, dependency, yearly and PCFG. So CKY and dependency are bottom up. Even PCFG is bottom up. Only yearly is top down. Here CNF is used in CKY. Here dependency rules. Any CFG can be used in yearly. PCFG with probability values. So handling ambiguity, all parses, code passes, all passes, best probability. So it will based on the best probability. So complexity, almost everything is same. Early processing, worst case, it is order of n3. Otherwise, it is order of n. So basically, early parser is good in terms of complexity. Best for exact parsing, relation extraction, flexible grammars, and disambiguation. So the summary which we have seen from this presentation is you have learned about what is CKY parsing, the introductory part of CKY parsing, dependency parsing, yearly parsing, and PCFG. So, as a conclusion, the parsing techniques are the heart of how machines understand human language. So, by analyzing the syntactic structure, parsers enable computers to move beyond surface level word matching towards genuine comprehension of sentence meaning. From the algorithmic elegance of CKY and early to the linguistic effectiveness of dependency structures and statistical power of PCFG, these methods collectively form the backbone of modern NLP pipelines powering translation, search, dialogue systems, and beyond. So, the parsing bridges the gap between raw text and structured meaning, enabling the machines to truly understand the syntax and sentence structure. Thank you.